Okay, we're going to take a look at the ELTE131 final exam review. So this class, we covered a lot of material. So I'm going to go over the final exam review worksheet, but the issue is you really need to understand everything that was in the week or the unit. So the best way to do that is to take a look at the week. For example, in week 2 here at the beginning, there's a paper, and it tells you everything that you were supposed to learn this week. So I would start by going each week, week to week, and taking a look at the module guide sheet and being sure that you know what these things mean and that you can answer the questions related to all these things, okay? So with that said, I'm going to go ahead and go over this final exam review sheet. And I remind you that these are not items that are on the final exam necessarily. This is just concepts related to the things that are on the final exam, and hopefully they make sense to you. So let's work backwards. We kind of finished up with sequence of operations, and we'll work towards week 1. So number 1, what are 2 ways to stagger control of 2 motors? So if we want to stagger controls, like have one start after 30 seconds and then another one start 30 seconds later, well, we can cascade them with 2 timers, or we can put the timers in series. So what that would mean would be that we would have something starting the first timer, right? And then this timer could have some contact that started the second timer, okay? So let's say this was normally open, timed closed, and that was the 1 TR. So if this was 15 seconds and this was 30 seconds, well, this timer would come on, and after 15 seconds this would close and the second timer would come on. And then there's contacts associated with these, time contacts and instantaneous contacts that you could use in your ladder logic, okay? Or what you could do, you could turn on the first timer, and then you could also turn on the second timer. And remember, there's something turning these timers on, whether it's a push button or a relay, or in this case, in the top one, let's say a relay turned on the first timer, the first timer turned on the second timer. In this case, maybe this would be the same relay, and they would turn on both timers at the same time. And in this case, this one would be for 15 seconds, and then this would be the addition of the 2, which would be 45 seconds. So something could occur after 15 seconds, and then something could occur after 45 seconds. So these are kind of in parallel. These are kind of in series because one starts another, cascading. Okay, and then knowing how all the contacts work to start the motor or control your devices, that was what we learned about. Next, it said draw the control logic for 1 PB momentarily causes the cylinder to extend. The cylinder activates the limit switch. So there we go. 1 PB causes the cylinder to extend. So we come right here and we did a start. We could turn on a control relay and we could put memory on it. That's 1 PB. So there you go. You've got memory on there. And now it says it causes the cylinder to extend. So let's use that control relay to turn on a solenoid. And that is the solenoid. Let's just say it's a 5-2 single coil. So then it's going to extend. Cylinder is going to extend. The cylinder extends, and apparently it's going to hit a limit switch to indicate that it's extended. And so that limit switch is going to start a timed relay. Okay, this is the 1LS. This means that the cylinder has extended. This is going to count 5 seconds. And then what do we want to do? We want to retract the cylinder. Well, let's not put it here. This would be a place to put the contact to cause that to go off. But let's just stop the whole process because we have memory here. So if we open up the memory here, and we had a normally closed time to open, after 5 seconds, this would open, this would go off, that would go off, that would go off, that would retract, and it would walk off that limit switch and everything would be back to the way it started, and then we could hit this again. So that's an example of using the timed relay there. Okay. Draw the following control circuit. 1 PB activates CRL and an amber light. 2 PB activates, unlatches it. Okay, that should be CRU. Sorry. So we don't need a parallel holding because we're using a CRL. So we would have 1 PB activates 1 CRL. Okay, and apparently turns on an amber light. So we could have the CRL contact turn on an amber light. 2 PB activates the CRU. So here we've got 2 PB doing CRU, and those are the same relay there. 2 PB activates C and a red light. So basically when I hit this would unlatch it and that would go off. But at that point we want something to turn on, so it looks like we must be using the contacts from the CRL to turn on a red light as well. And this would be closed. So therefore, we either have this on and this off, or this on and that off. Okay? And then if we're using this diagram right here, we want the sequence of operations that we went through. So let's say we had the disconnect off. Well, we assume nothing would be happening. Disconnect on. Well, we haven't pushed anything, but at that point we have the this contact closed, so we would probably have the red light on. Okay, so we could fill that in, probably the red light on. Okay, 1 PB is pressed, so while we're pressing it, we get the CRL to come on. Okay, the CRL turns on the amber light, and then the red light goes off. We release it because it was latching. The CRL, or the amber light, stays on. Now the CRL is not energized, so I'm just going to kind of put a little square on this because it's not energized, but it's still held on, but not an energized state away. It's the mechanical that held it on. If I killed the disconnect at this point, well, everything's going to go off. But I'm going to put a little square around this with an X because, once again, this is not energized, but it is latched on, okay, because mechanically. But there's no power to anything. That's why we don't have any of our loads on here. Let's turn the disconnect back on. It's held. The amber light comes back on. This is still held mechanically. Remember, that's the difference between a mechanical latch. You kill the power and then you turn the power back on, it comes back on. If we would have had a holding circuit here, it would have went off. 2 PB is pressed. Well, so when I push 2 PB, CR unlatch comes on. And that's going to turn everything, those off. And I'm a little bit messed up here. This red light would come back on. So where's my red light? This red light would come back on, that's right. Okay, because it was closed. 2 PB released. I'm going to have the same, this right here is no longer going to be energized, so it's just going to be off. My red light is still going to stay on because the power is off. Okay, and then if I kill the disconnect, once again, everything goes off. So that's kind of the sequence of operations there. What is a master control relay, and draw a control diagram? So a master control relay is a holding circuit. So the master control relay would have a stop-start, and it would have a start, like MCR on, and then that would go to your master control relay, okay? And I would have memory here. So this is my master control relay, like that. And then what we use the master control relay for is we have contacts farther down here that are associated with this. Okay, this is MCR. This is probably better known in this solid ladder logic as CRM. So maybe this would be control relay master, CRM. Okay, either one of those is a designation for those coils. At which point any ladder logic that we have down here, these lines, are now activated because these are closed right here. But unless you turn on the master control relay or the CRM, these are open, and then all the ladder down here, well, that's not going to be energized, so you won't be able to do anything. So that's how a master control relay works. So we have our time machine control. We went over the contacts here of how they worked, which ones are on delay, which ones are off delay. And so we have, just to remember, a normally open, timed open. So we start with the way that it's drawn, normally open. Well, this one's drawn open, and this one's drawn open. So it's one of these two. And then it's going to time to open. Well, this arrow is indicating to close, and this arrow indicating down, so that would be to open. So this is going to be number 1. Normally open, timed, close. Let's check it. This is open. The arrow indicates that it's going to move upwards, and it's going to close. Yes, so this is 2. The other thing about this is, okay, let's keep going. Normally closed, timed, open. Well, these are closed. Yeah. And it's going to be timed open. So the arrow here indicates that it's going to go down. That's not open. The arrow here indicates that it's going to move up, and that would open it. So this is going to be 3. And I bet that normally closed, time closed. This is closed, and the arrow indicates that it's going to move down, which would be closed. So this must open and then close. So it's normally closed, time closed. And then remember that these on delays here, they start timing when the coil becomes energized. When you get voltage right here, and that is energized, that starts timing, okay? Versus these are off delays. What happens is when you give the voltage to the coil right there, well, that's when they change states, immediately change states, but you have to then remove the voltage from that and de-energize it, and that's when they start timing and end up back to their normal position, okay? So that's the difference between those two. So that's basically, we went this, what does the contact tell you? That's the way to draw it, okay? Let's keep going here. How do you stop a cylinder piston mid-stroke? Well, we talked about the different type of valves. So if you have a 5-2 valve spring return, well, that is just 2 states. It's going to, for example, push air out and cause the piston to extend, or if we have the other state, it's going to push air here and it's going to retract, okay? So if you kill power to a 5-2 spring return, it would just return it, okay? So what you're going to need here is you're going to need a 5-3 valve, okay, with a center state. And so this center state, you would have to, while it was extending, you would have to kill power, which the spring would return it to the center state, and it might be teed off, and then the cylinder would kind of stop mid-stroke, okay? So that's how you would have to do it. You'd have to use a 3-position valve and kill the power mid-stroke. The difference between a double-acting and a single-acting cylinder, remember, a double-acting allows you to pressurize both sides of the piston here, and you can use the force generated by the air pressure to move it forwards and backwards. A single-acting cylinder might not have this. It might have a spring in here, and the air would push it out, the spring would return it back. The benefit of the double-acting is that you can get a lot more force here, and you can also get force here, a lot of force to push and pull that. Whereas if you don't have this one, you're relying on the spring, and if the spring isn't strong enough to pull this back, if it binds or something, then this gets bound and is extended, okay? Double symbol and advantage. So if we want the 2 coil, that's what we were talking about, a double symbol. I think what I'm doing is, that was my double. We just went over that in the single. The other thing you wanted to know once again was the valves, the 2-position verse, and this will be spring. the 5-2, let's say, versus the 3-2 or the 4-2. And so for a 4-2, that's where we were talking about, air was going to come in to this port here. It was going to shoot straight through, maybe like this. And then the other way, when it activates, it would be like that. So we did the fluid sim and saw how this changes between the two states to allow air to, let's say, in this case, it would put air here and it would extend out, right? But when it gets activated this way, you can tell that the air changes direction. So the air would, instead of going to the front here, this air would go to this side, and then this air would go to this side, and it would retract. So we went over how those 5-2, 4-2, 3-2, 5-3, 4-3, all those different valve designations worked. Okay. Motion. The difference between a capacitive and an inductive prox. Well, capacitive sense is just about everything. It has a dielectric constant of greater than 1.2. And inductive basically does ferrous or metal items, okay? So that's the main difference between them. How does the proximity field work? So all the proximity sensors used some field, whether it was sound or light or some type of magnetic field. And basically the field gets interrupted when you move something in front of the field. And the sensor's solid state, and it's meant to sense slight changes in the field. And then you get sensing of the item, even though you're not actually touching it. You're just interfering with the field of the specific proximity sensor. Okay. Wire through beam optics instead of retro use on conveyors. Well, on a conveyor, you would have, a part rolling down this conveyor. Let's put something on there, going this way. So a through beam, if you just want to count it, that's pretty easy to do. You would have an emitter here and a collector here, and you just shoot a beam of light across there. And then this will break that beam pretty simply. It doesn't matter, what your working environment is here, if this is greasy or if there's something, kind of in the way or not. I mean, this is gonna absolutely break it, and then it's gonna open it up again. Okay, whereas if you get a retroreflective, you could get some variation on this right here, and it might not bounce there wouldn't be a collector in that case. It might not bounce it back to the collector here. We had a retroreflective. Okay, this is just simpler. It's easy, and it's almost bulletproof to sense things coming down a conveyor. Okay, and we went over all the different motion sensors about how they worked, and you'll want to review the lab solution that I gave you. Ground detect. Draw a start-stop latching motor control with a ground detect and examine the light indicator at 3 different grounds. So that was where you want to take a look at your lab again and the solutions that you were provided, where we had control relay like this. So there's a memory circuit, start-stop, or stop-start control relay. And if we had our ground detect lights, and we had a ground here. These were my lights. Okay, let's say they're red lights. I made them. So that's where we talked about, well, what happens if you get a ground detect, at this location here, right? And then, whether buttons are pushed or not or whatever. In this particular case, we had ground detect here, and we hadn't pushed anything. Well, there's flow through this button because it's closed. There's no flow through that because it's open. There's no flow through that because it's open, and we haven't hit that yet. But there is flow through here, okay? So this electricity is going to take the path of least resistance right through here. And it's going to, instead of going through 2 lights, why not just go through 1? So this is going to get bright, and then this is going to go off, okay? And then we talked about, well, what happens if you push the button here? Well, when you push the button, this is going to close, and you let it up. So you would get flow through here, so this control relay would be on, right? But at that point, you just got 2 items in parallel. You've got flow this way, and you've got flow that way. So the control relay would be on, and this ground detect light would still be on. So we went through the analysis of how the ground detect lights worked, and you were given solutions for that. Draw the connections for a reversing motor starter below. All right, well, we can do this like this. So here's my line. If I just had a single starter, my connections would be easy. It would just run line 1, line 2, line 3 into the main contacts, and then these would just run up like this. Okay? And you'd be all set. So now what we want to do is we want to reverse it. That means we need to, flip 2 of these contacts, okay? So let's start by a look on this other side over here. So what we would do is let's just first jumper these sides. So this one was just jumpered to there, and the middle one was just jumpered to there, and the left one was jumped to the left, okay? So still the voltage is coming through, and it's just then running to the motor. But what we need to do on this side is we need to mix the voltage up. So instead of the top, the right going to the right, we switch the right to the left. The middle still goes to the middle, but then the left goes to the right. So in this case, if we went forward, well, you see the left goes to the left. But if we do the reverse, you see the left goes to the right. So what we've done is we switched 2 leads, and that's how you reverse a motor. Is just switch any of the 2 leads. Okay. What's the difference between plugging a standard reversing circuit and a plugging circuit? So the reversing, what you would want to do is you would have to hit stop, and then you would then reverse it. Okay, so hopefully you would stop it and let the motor come down and stop, and then you would, at some point later on, you might want to run it in the opposite direction. I don't know in that case if you just want to automatically go from forward to reverse. If you just automatically, for some reason, want to go from moving forward and slam it in reverse, that's when you would use a plugging circuit, okay? You don't have to hit the stop button first. And you might plug for a while using a centrifugal switch, or you might plug using a timed relay, so that basically you would use that to slow the motor down, okay? The reverse operation. And then, so draw the plugging circuit. That was the second circuit from week 8 that had the push button interlocks, so that you could push the forward or reverse while it was running forward or reverse, and it would switch direction. They were interlocked. You couldn't push them both at the same time. That wouldn't have mattered, but you could reverse. What is an interlock, and why are there three different types of interlock? So an interlock is going to prevent 2 operations from occurring at the same time, right? So what we had there is we had the push button interlock. So we had, a closed push button here, and it was interlocked to an open push button here. So when we push the open, when we push the open to close it, it opened to this one. So you couldn't have this one closed and this one closed at the same time. You either have closed and open or closed and open. Okay, push button interlock. We had electrical interlocks, and that was where you had a control relay like this, where you had the contact. So when you turned on a control relay, this opened and this closed, and when you turned it off, this was closed and this was open. You couldn't have both of these on at the same time. That was my electrical interlock. And then the other one we had was the mechanical interlock, where you had the forward and the reverse, and you had the little line there indicating that they were mechanically interlocked. So even if you tried to energize them, if for some reason these failed and both of these got voltage to them, then they're mechanically set up that you can't close the contacts forward and close the contacts reverse at the same time, because inside of here, right here, there's a mechanical device that prevents it from sliding or from energizing both at the same time. So those were our interlocks. It says, draw a circuit with a parallel jog push button. Okay, we can try this. So if we wanted to do that, we would have a jogging circuit. So the best jogging circuit is going to be the one where we want, the jog run, we would have, a start right here. This is interesting. And what we might have is, here's my motor starter. We could have my motor like this, right? And what we would do is we would put in a jog button in there, okay? So in order to let's fix this again. Sorry, we have a motor. What we would have here would be some type of a selector switch. I'm sorry, that we could selector this function on or off right here. Okay, so that if this was clicked up, basically what we've done is we've created the opportunity to have memory here on the circuit. And when we open it, well, then we don't have memory, so that this button would act either as a run or a jog, depending on this, okay? So now, if you wanted to draw something with parallel jog push buttons, I suppose you would, that would be a run. I guess you could put another push button here. Maybe you'd have to hit the selector and hit the jog button. Or down here, you could have a jog button number 2, and maybe you put some memory, and you could use the selector switch here, that it's tied into both, okay? So maybe I hit the selector switch, I could either jog from here or jog from here, maybe something like that. There's other ways to do this. Why would you want to do this? I'm not sure, because the issue is if this jog button here could get the motor to jog, and this button here could get the motor to jog, well, that's probably not good, because this person here might not understand what this person's doing at the time, and this person might not know what they're doing. So you wouldn't want somebody working on the motor and having this person who's supposed to be pushing the button, pushing it, but when they're working on here, the person who's not supposed to be pushing the button, push it. It could jog. So yeah, maybe not a good idea. Why is jogging necessary? Well, jogging or inching the motor basically gets it to turn a little bit. So sometimes you want to turn the motor without destroying it. Maybe, for example, if you were winding something and then you got something all caught up into it. For example, I was running my vacuum sweeper the other day, and the kids rolled the vacuum sweeper over a power cord for a computer. Well, the vacuum sweeper just chewed that cord up, and then it bound, and it was all jammed in there. Well, too bad my vacuum sweeper wasn't 3-phase. Otherwise, I just could have jogged it backwards slowly, a little bit hit at a time, and tried to unwind that cable. Okay, instead of just, jamming it into reverse. But if it was single phase, I couldn't do that. But maybe something like that could happen on a 3-phase motor. Or maybe you were trying to line up a coupling or something, and you need to turn the motor just slightly, a little bit, until those lined up. Okay, so there's a variety of different reasons why you would want to just kind of, inch that motor forward a little bit, okay? Contactors and starters. What are the parts of an overload relay heater? So we went all the way over of how these worked, and remember what we had a contactor, and then when we added an overload to it, basically when you add those two together and put all the auxiliaries and everything, you get a motor starter. When these are all built into one unit, a motor starter, okay? And so the basic parts of this contactor right here were going to be the contacts. Remember, there was going to be 4 contacts on here. There was going to be 3 main contacts and an auxiliary contact, right? And then this overload was going to have a heater and was going to have overload contacts, probably normally open and normally closed, okay? And then the motor starter was kind of all this put together. Maybe there was even more additional auxiliary contacts and stuff like that. So what are the parts of this overload? Well, that was the overload where we talked about the different types of overloads, such bimetallic. We broke down all the 3 thermal, but when on that situations what we're talking about. We talked about how the paw and the catch and the melting alloy, and it how allows that to spin, and then it opens up the overload, which is the open overload contacts, not the heaters. The heaters don't open, but the normally closed overload contacts open, and that's used in the control circuit. Okay, so those were the parts. And then it cools down, and the fluid, the alloy solidifies, and then you can push reset. So the whole operation of overloads and how they worked, and how when we built control circuits and we put the motor starter and then we put the overloads here, the purpose of that was to bring down the motor starter. And when the motor starter comes down, the memory comes down on the control circuit. So that goes off. Okay? And that way it won't automatically restart. And then this overload had because this went down, the main contacts went down, right? But the overload was part of the power circuit. It had the heaters up here. And when they heated up, that's what caused that to open. These don't open. These are just heaters. That opens, which opens that, which opens the motor starter contacts. That's that device there. These devices are together. These devices are together. But when you put them all together, it's called a motor starter, but they still act independently of each other, okay? They're different items all combined into one. What's the difference between 2 and 3 wire control? So 2 and 3 wire control. So 3 wire was when we had memory. And the purpose of that was that when the power went off and the power went back on, the item wouldn't start back up. It would have to be reset. An example I gave was my table saw at home. It's just got a switch. It turns on or off. So if the power went down, or if I blew the circuit breaker, the saw would go off. That's 2 wire. And if I pushed the circuit breaker reset, the saw would start right back up because it only has 2 wire control. But now bigger table saws have a relay in them, so that if for some reason you're running and you blow the circuit breaker and the saw goes off, that means that the contactor goes down, the auxiliary contact goes down, and the memory goes down. So when I reset the circuit breaker, it doesn't reset there. Draw a start-stop ladder using 3 wire to energize a relay and amber light. I can do this. We've been doing this a lot even just now. So that was my stop. That was my start. And this was my control relay. I have memory. And then an amber light. So somehow I'm going to have a control relay and I'm going to put an amber light right there. Okay? So there you go. Remember, if that amber light is always on when the control relay is on, I might have been able to just take this step out here and put the amber light right there. It's the same. But either way, that would accomplish it. And then we learned how to label your wires here, 1, 2, 3, 4, etc. And then we learned how to do the contact designation that this control relay, in this case, would be used on 2. And it would also be used on 3 right there. And if I put a 4 here and I had a closed contact, let's say that did a green light for some reason, that would be 4 underline, meaning that it's closed. So we learned about how to do all that stuff. If the start button has been pressed and then released in the above circuit, what is the resistance across the start button terminals? Okay, so here you go. We want if the start button has been pressed and then released, what is the resistance above the start button terminals? Okay, so if it's been pressed and released, that means that this right here is true because it's running. We hit start and it's running. So if you came in here while it was running and you tried to get resistance between here and here, that's where it's asking between 1 and 2. Well, you're not going to find any resistance because you'd actually be measuring the resistance across this here. And because this is closed, you would get 0 resistance, right? Now, if you broke this item out individually, you took this push button and it was open and you checked the resistance across that, well, that's where you would get infinite resistance because it wouldn't be open. Or if this system was de-energized, then and you measure across there, you would get infinite, because it wouldn't. This would be open and this would be open. But once you energize it, once you start it, you got to remember, like, if I'm checking resistance, what am I checking? Am I checking this, or am I really checking this device, or am I checking through the transformer? Things like that. What's the difference between low voltage control and a power circuit? So that was where we were just talking about right here. The power circuit was up here. The control circuit was down here. We use the control circuit down here to close the main contacts on the power circuit. Okay? And we use some sensor here. This sensor would break the continuity or remove voltage to the motor starter in the control circuit. The motor starter would then open up the power circuit. So that's the difference between my control circuit here and my power circuit. Okay. What's the difference between a rung and a rail? Well, since we were going backwards in this review, it seems like things are getting pretty simple, right? So we have my rails here, which are indicated by line 1 and line 2. And then we would have my rungs across here that would have my ladder logic in them. And we talked just a minute ago about how to cross-reference a rung. It would be the numbers on the right side here. Our ladder diagram numbers, fictional or real? Well, just as we talked about right here, when we put these wire numbers on here, we would expect that when we went and we looked at this item, that this number, this wire here, for example, that was 5, on this end of the wire and on this end of the wire, we would expect to see a 5 on either end so that we could troubleshoot this, okay? So the actual wiring of the item should match what the ladder diagram is showing. Symbols. What are 3 sections of a control diagram? So what we had on the control diagram, we kind of had on the left, a lot of times you have your inputs, and on the right, a lot of times you have your outputs, your field devices. And then in the middle or other, typically, but it could be a little bit different, is the logic commands, where your control relay contacts or your timed relay contacts and stuff like that might be more situated here, in the middle, but not always. But the loads you're always going to find the loads or the output devices here on the right, okay? And so your examples of inputs would be limit switches and push buttons, proximities like that. Your example of your outputs are going to be your lights and your control relays and your contactors, solenoids, stuff like that. And then, like I said, in the middle is going to be your timed relays, your control relay, normally open and close contact, stuff like that. Interlock push buttons. So we talked about that if you had a push button that was here, and then you had another one that was here, whether it was open or closed, it'd be a dotted line like that, right? You get a dashed line between them. Not dotted, but dashed. How many contacts can a single push button have? Well, believe it or not, a push button can have a lot of contacts, because what you have is the actual physical push button that might look like this, right? And then on the back of it, you get a contact block with a couple of contacts. Well, you can just stack another one on there if you want. You can stack another one on there, and you can stack another one on there. And then they're both two-sided typically. So on this side, you could stack one this side, this side, this side. You can just keep stacking contacts, any combination of normally opens and normally closes that you want. You probably wouldn't want to stack like 1,000 or 100 or 50 or even 20. You know, typically you might see some of these with 2, 3, or 4, maybe at the most, but you could have a lot. So we used JIC. So those were the symbols that we have been studying. You want to understand what those were, and those are all the push buttons and control relays and limit switches and all the designations and everything like that. Those were this week, and you want to know what they are. How does the gravity rule apply to switch designation? Well, remember, you kind of say, well, what would, if there was a switch below this catch here, what would it do? Well, it would fall open. Okay, that's a limit switch. It would fall open, and that would be in the normally open case. Whereas if you had a switch, that was up here, what would happen? Well, it would fall. It would fall until it hit that right there, and then that would be your limit switch and that would be a normally closed limit switch. And then we talked about a lot of switches look like this with the gravity rule, but there's a few that don't apply to the gravity rule, and that's like the foot switch, you know, where you would, like a sewing machine, you would slip your foot in there and you would press it and it would close. So in this case, the gravity rule doesn't apply because this is a normally open foot switch right here, okay? But most of them apply the gravity rule, and we study that quite a bit. Transformers. So our lab volt trainers plug into 208 three-phase. What voltage are available on the fixed side of the trainer? So we got 120 because we got line 1, line 2, line 3 to neutral is 120. And then we've got 208. And what type of transformer? So you're going to, if you looked at all your voltages, you would find that this would be a Y, okay? And so for this section, what you're going to need to do is you need to take a look and understand your common Y and your common delta voltages, okay? Whether they're 120, 208, 277, or if you're looking at some deltas like 240, 480 on your deltas, take a look at that, and you want to get a rough or a pretty good knowledge of what you're going to see. If you see 480 volts, you're looking at a delta, okay? But if you're looking at your 208, you're seeing a Y. Are you more likely to find 3-wire Y or delta transformer? So once again, you want to draw the list of voltage. Are you more likely to find? Well, it's going to be depending on what your application is and what your devices are and what's available in your facility, okay? But you want to know what these are. And there's going to be some here that aren't very common, but you're not going to really need to know, what's the most common. You're going to want to know what those are. Are you more likely to find a 4-wire Y or a delta transformer? So once again, you're going to want to go and you're going to want to draw the list and understand the different voltages for each one of these right here, okay? And in this case, I'm going to say you might find 4-wire Y more often. The deltas might be 3-wire, okay? And so the deltas, just might be 3-wire. That they talk about the wild leg, center tap, and all that kind of stuff. It might be more common to find a 3-wire delta than a 3-wire delta might be pretty common. So a 4-wire delta probably going to be more common a 3-wire. But we're not going to get into that. I just want you to know the list of the voltages. What is the scientific term that allows transformers to work? That's mutual inductance. And so basically that says that if you run a current through a coil, you get a magnetic field, right? Current through a coil, you get a magnetic field. And on this side, if you wave the magnetic field in front of a coil, then you get current. So current makes magnetic field makes current, okay? And remember, this magnetic field needs to be collapsing because that means it needs to be alternating current because it needs to go plus and minus, because this field needs to keep expanding and waving in front of this magnet. So mutual inductance is what that is. What's the difference between the dual, primary, and center tap transformer? So a dual primary is what we use quite a bit of. And remember, you learned how to designate this and draw it. And when you wire it in series right here, you're doing a 4-to-1 step down. But if you were to wire it this way, you would be doing a 2-to-1 step down. Okay, that was the dual coil. The other one that we did on the lab volts was the center tap. And so the center tap was where you had your primary here, and then your secondary had just different voltages that were tapped off here, so you could get 40, 80, 120 volts on this side, depending on if you brought in 208 over here. So these were center tapped. You couldn't change. You couldn't change them. You couldn't change them on the other one either. But you just picked off the one that you wanted. There was no jump ring. Okay. In the primary and the secondary side, primary is where you're bringing in your voltage, and then the secondary is the voltage that you wanted conditioned or brought usually brought down to the level that you wanted for a control circuit. Okay, so you brought in 208, and then you wanted 120. That would be your secondary. We talked about the turns ratio, and that the power in on this equals the power out. Or to say it again, the VI in equals the VI out, right? Volt amperes in equals volt amperes out. We did some calculations on that on the transformer. So if you have if you have lower voltage on the secondary, you're going to have higher amps, and higher voltage here is lower amps because the two must multiply and to be equal. Okay, so we've got some stuff in the reading that we went over that. So what's the resistance of an open contact? This is just some 108 review. On open, you'd be thinking that would be infinite. What's the resistance of 4 ohm loads? Okay, well here we go. If they're in series, it's going to be 4 plus 4 plus 4, 4 plus 4 plus 4, and that's going to be 12 ohms, right? And then in parallel, well, that gets a little interesting. So we'd have 1 over 4 plus 1 over 4 plus 1 over 4 equals 3 over 4. And then we need to flip it. 4 over 3. Okay? So that would be 4/3 ohms. And then in series parallel, that means we're going like this, I guess, where we have a 4, a 4, a 4. And so what do we need to do? Do our parallels first. 1 over 4 plus 1 over 4 equals 2 over 4. Flip it. 4 over 2. Well, 4 over 2 in my book is 2. So I'm going to simplify this and make it, excuse me, that would be 4. And these simplified into 2. So 4 plus 2 would be 6 ohms. And so you're going to want to just review, what happens on my voltage drop here, which one of these is getting more voltage, what happens to the current, things like that. Just review some simple series parallel circuits, just like I've shown there. It says that the voltage drops to the resistors in a, what is the voltage drop? Yeah, so you're going to want to go ahead and take a look at what these are. So, for example, in series, the voltage drop is going to be equal. So each one is, let's see, you want 12 volts, you get 4 volts, 4 volts, 4 volts. In parallel, well, the voltage stays the same, so each one would drop 12 volts. And then series parallel, you could work the math like I said. You want to take a look at it. Complete the chart. Voltage, the unit is volts. Current is amps, ohms, and watts. Volts, amps, ohms, and watts, right? And the symbol would be V or E. Current would be I. How about that? You might get A on there, I or A. Resistance would be R, or maybe the upside down horseshoe. Or power would be watts. The symbol would be P or W, right? W or P, that's what you might see, okay? That's just a review from 108. Consider the diagram assuming a 12-volt source, and when the switch is closed, what is the resistance on 1 and 2? So I have 12 volts here, 10 ohm load, so this is 10 ohms, okay? Switch is closed, what is the volt reading on 1 and 2? So, okay, so I'm guessing that we're energized. So if we're energized, we got to be careful what we're reading here and think about it. What's the voltage reading on 1 and 2? So I got plus here, and I'm coming outside, I got 1 here. So if I checked the voltage between here and here, I would get, I've got it plus to minus, I would get 12 volts, right? And same one on this one, when the switch is closed. Oh, hang on a second, that's my own, I see what I'm talking about. Yeah, I would still be the same there. The switch is closed. On this one, I would get back to here, and I would get back to there, okay? And there's a load here, so I would get 12 volts. What's the resistance reading on 1 and 2? So if I'm with the switch closed, am I reading the resistance here? Probably not. I'm probably reading the resistance back around this way, I could, or I could be I'm getting a parallel load. We don't know what it is. It could be ugly. If this is closed, same thing. These meters are essentially doing the same thing because that switch is closed. This meter could be here because this has no resistance. We're either measuring the resistance of the battery, we're measuring the resistance of the resistor, or we're measuring some combination of both. So with the resistance, we don't know. It's probably something messy. When it's open, when the switch is open, that's different. Because when this opens right here, okay, well, on number 1 right here, I still have plus, and I still have a path to minus, so I can still get 12 volts. When this is open, for number 2, I have a path to this side, but I don't have a path here because that's open. So I would say 0 volts I would get there. Measuring resistance, well, if I look at 1, if this was open, it looks like I'm measuring the resistance of the battery. So that's not good as a voltage source. Who knows what we're going to get. When this is open, number 2, well, I'm on this side of the load and this side of the battery, so I could possibly be doing either or. But on this side, this is open, so I'm really only measuring this, and I would get 10 ohms. Okay. So we talked about how to troubleshoot like that. We did a lot of it. How do you get incorrect readings on the analog and digital voltmeters, and we talked about calibrations and how to calibrate Simpsons and stuff like that. So that's stuff you want to review. So the circuit connections that you'll want to take a look at from week 7 and 8, because they might be referenced on the final a little bit, are the jogging using a selector switch, jogging using a control relay. That seems like that was the hardest one for people to do. Non-plugging and plugging using the forward and reverse circuit. So you want to take a look at those labs, okay? So, just want to remind you, this is just a quick walkthrough of what we learned. If you really want to think about what we did, I recommend that you go to each week, and then you would go to the sheet. Let me get through there. And take a look at the module guide sheet. And there it tells you what the module outcomes are, and see if you understand most of what this is saying here, okay? And also take a look at the notes on the reading, because that talked about a lot of what we studied. So that's a quick overview for the final. There's a lot on it, and you should study quite a bit.